So it is my great pleasure and honor to visit old friends, meet new friends. Today I had like really exciting tours on this like really world-leading, not only meeting world-leading scientists, but also like learning from the world-leading centers and facilities that this campus is developing. So it's really exciting. So I should say that although we would claim that we do atomic scale, we're probably not actually seeing things in atomics, such as your like wonderful microscopy center. We're trying to study structural dynamics phonons, probably not as what we can see in X-ray facilities. We're trying to push the materials hard, but probably not as hard as your high pressure facilities. But again, this is a pretty good a tabletop system where you can actually engineer materials as properties pretty conveniently and move the atoms around. So it's really my great privilege to talk with this audience today. So here the topic is called chiral phonons. So this actually we developed first at Berkeley, actually with Robert, and then later this field kind of evolved because just think about that, like phonons, right? So if you study solid-state physics, there's basically atomic motion, right? But then how would phonons become chiral and how is it useful? So eventually, potentially for nowadays, most important technological problem is like how we can improve, say, devices, information technology, right? So Spintronics as an example. So these phonons will be relevant there. So from fundamental science perspective, chiral basically means handed, okay? So, what object can you think about in your undergraduate education that carries the term chiral, right? So chiral molecules, you probably even learned from high school chemistry, right? So if the molecule is different from its own mirror image. Okay, so just like a carbon center and it has 4 different bonds, it's chiral molecule, right? Then when we enter into more like condensed, more advanced physics, you hear like there are chirality that's defining high energy physics. You also hear a lot of chiral objects that has been defined or at least mentioned in literature in condensed matter physics. Okay, so more recently is people talk about chiral superconductivity, so chiral wire fermions, like chiral edge states, etc., right? Topological edge states. So these terms all called chiral. But if you look at their actual properties, so by bearing the term chiral, what can you predict from the term? Their property are actually very diverse. Okay, so even from a very basic symmetry perspective, the chiral molecule basically says you're breaking mirror symmetry. Okay, but then so chirality high energy physics it breaks some other symmetries, whereas the different type of chiral objects in condensed matter breaks a variety of symmetries, including inversion or time reversal, or both of them. Okay, so that given that complexity, one would ask the question whether we can define chirality for phonons, which people have not thought about, and how could that definition be useful in physics? Okay, so is it actually breaking mirror or inversion or time reversal, and what's the consequence of that? So here is an example of how phonons or atomic oscillations within a solid state materials can break all of the symmetry. Okay, so of course, in lattice crystals, atoms never move far away, right? They can only move within the unit cell, right? But they can imagine if here is an atom, and then it rotates a little bit, just near its equilibrium position. Okay, and that of course breaks time reversal because rotating left and right are different. That can break mirror symmetry if also this phonon can carry a finite momentum. Okay, so how can atomic motion carry linear momentum? Just similar as how electrons carry, like in band structure, carry momentum. The atoms in each unit cell actually move in slightly different phase. And then you can prove that this type of rotation definitely breaks, in this case, this is X mirror symmetry. In similar manner, this rotation breaks Y mirror symmetry. And then because there is a phase difference along the Z axis, these type of phonons also break Z symmetry. So essentially, this is a helical rotating atom that breaks all this mirror X, Y, Z and time reversal symmetry. Okay. So this object definitely can be named chiral. So it abide with all the conventional definition of chirality. So we can think about some other phononic modes, atomic motion, that breaks slightly less symmetry. So for example, if I have a crystal, which originally has mirror symmetry, and then I pull this atom towards the mirror, what will happen? Then if you perform a mirror symmetry, then of course the structure keeps the same, but the atomic pulling direction is reversed, right? So the action of pulling that atom is breaking mirror symmetry. And then it makes a structure chiral. So one can prove that in some crystal structures, moving atoms would cause the structure to become one of the chiral point groups. Okay, so there are in total 32 point groups with for 3D crystals, and then there are more than 20 of them are actually chiral. I think 22, and then pulling the atom left or pulling the atom right would place the structure into the left-handed point group or the right-handed point group. Okay, so these type of phonons are definitely chiral. So if you're moving atom, you make the structure breaking mirror symmetry. But this process doesn't break time reversal. It's a static structure, right? So that complies with the definition of chiral molecules. But doesn't comply with the definition of, let's say, chiral edge states, because it doesn't break any time reversal. Okay. So similarly, there are atomic motions that just pull the entire structure into a weird shape. Okay, it doesn't belong to a chiral or left-handed or right-handed point group, but it also breaks mirror symmetry. So you cannot say whether which state exactly left or right, but this shape of the crystal actually deforms into chirality. So that's one category, like static. There are also phonons that breaks mirror symmetry in XY direction. It breaks time reversal, but it doesn't break a mirror symmetry in Z direction. Okay, so these type of phonons, technically, you can put them into like a two-dimensional space, right? Because in two-dimensional space, Z direction operation does not exist, right? Okay, so in that case, then just an atom rotates in two-dimensional space would actually break all relevant symmetry. So we can call it 2D chiral. But then the same mode, if you put in three-dimensional space and consider z-axis, then it won't be chiral because it has like mirror symmetry with respect to the plane itself. Okay. So there are other type of atomic rotations in three-dimensional space that only breaks time reversal. Okay, so it preserves mirror symmetry, and in those cases, it would have similar symmetry to cases like chiral superconductivity, but it will not have the same symmetry as the chiral molecule. Okay. But in any case, so we think that because all of these like atomic motion break some symmetry that would be able to predict that a finite coupling between the phonons and the object with the same symmetry group, we would like to just call them all chiral phonons, and then basically name the phonons into roughly two parts, two groups. So one is that it breaks a geometrical chirality. So that is the mirror symmetry in XYZ. And then the other is called axial Phonons, which breaks time reversal. And basically says that it's a dynamic object that carries finite angular momentum. Okay. So, so these phonons would couple to for the importance of this talk, an object that we're interested in devices, that is electronic spins. Okay. So what happens is, if you look at the symmetry of electronic spins, it actually breaks time reversal. And also, if you can imagine it as like self-rotating, then it breaks the X and Y mirror. Okay, so these spins actually have the exact symmetry as the two-dimensional chiral phonons. Okay, so, and then it would mean that once you have a system and you inject spin, it will be able to convert to all this phonons listed in with this symmetry, and also you can convert the phonons. The atoms can actually kick electronic spins. Okay. So the geometrical chiral phonons, they do not necessarily couple with spin by themselves. But if you do a symmetry analysis, if there's some external field that breaks time reversal, then you would, for example, apply a current. And then the current passing through these chiral objects would actually have the same symmetry as spin. So that will naturally generate spin and vice versa. Okay. So that is basically saying that in any condensed matter systems, one would need to consider the chirality of phonons whenever you talk about spin phenomena, and if the system exhibits strong spin lattice coupling or electron phonon coupling. Okay. So that, and those aspects has long been neglected over many, many years until more recently, like theorists kind of pick up the concept of different chirality in condensed matter. So not very long time ago, 10 years ago, we had the first theoretical prediction of actually very simple honeycomb lattices hosting two-dimensional chiral phonons where the atoms actually rotate unidirectionally within the lattice. Okay, so then obviously it breaks time reversal, it carries finite angular momentum, and then the theory predicts that these type of phonons actually strongly couple with the spin orbital states of 2D materials, and thus it can be coupled with light. Okay. So why these phonons are important? Think about that. So traditionally, if people want to operate spins, okay, what do? Okay, you have a piece of magnetic materials, right? So and inject spins, or you can think about another object such as circularly polarized light, which has essentially the same symmetry as a spin. Okay. However, if people attempt, of course, the benefit of using light and spin to couple with each other is because now we have a technology for so-called ultrafast optics that can manipulate spin presumably in sub-picosecond or even femtosecond time scale, which is pretty good for devices. But then if you actually put circular polarized light into materials, you'll find that usually they talk like very weakly with spins. Okay. This is pretty much because for most of the light matter interaction actually relates with the dipole, electrodipole interaction with materials. And magnetic dipole interactions actually orders of magnitude smaller. Then if we can imagine if there is an is there a mediate, such as a lattice, which couples strongly with light, and the mediate, in this case is a phonon, also strongly coupled with spin. So all these processes are in principle symmetry allowed, but then from a detour, that coupling is stronger, then it would enable ultra-fast optical manipulation of spins. And vice versa, you can have ultra-fast spins that emit light. Okay. So this type of a phenomenon would be very useful, for example, and people have demonstrated that for generating or storing classical or quantum information carried by phonons through light. So in this case, then basically you can use red circle, left circle polarized phonons or different chirality of phonons to represent, say, information 0 and 1. In fact, this process can also be quantum coherent. So the other benefit of converting or controlling the symmetry of the material, especially coupled with spin, is a potential of actually manipulate materials and creating so-called non-equilibrium or materials like far from non-equilibrium that have special properties. So for example, people have previously demonstrated that if you just pull atoms and change the structure, then of course you can tune the topology of the material, or in certain cases, changing structure can also create superconductivity or ferroelectricity, etc. And then one can imagine that if I control atoms that breaks time reversal, okay, then would it be able to create, let's say, chiral topological, say, wild fermions? Or would it be possible to create chiral superconductivity, right? So these are all possibilities, right? So then, of course, these are pretty exotic, and we would like to study from a very simple point, that is, demonstrate that the spins and phonons can strongly couple. Okay. So that has been kind of attempted in the field of ultrafast spectroscopy. That is, if you shine light and somehow light drives the atomic motion because atoms are ionic, right? So it couples with an electric field of light. So these are electrodipole coupling, which is pretty strong. And then light drives the atoms to move, and then the atoms will affect the spin of magnetic materials, okay? So that's easy to understand because all this, if you already have a starting point of magnetic materials, they will have spin exchange coupling that depends on the structure of your material, right? Okay. So if we shake the lattice, then of course magnetism can change. Okay? You can generate magnons, you can inject spins, you can even create or facilitate a magnetic order. But then for all these previous ultrafast experiments, you have to have some magnetism already within the system. And then we would like to ask, just from pure symmetry perspective, it would be really nice if you can create magnetism or some spin phenomena by these phonons without the system being prior as a magnetic materials, right? So you create magnetism from nothing, okay? And that can also have been somewhat demonstrated before, or at least indicated by experimental evidence. For example, people say that if you have magnetic materials and then there's a basically insulator, a boron insulator, and then they find that somewhat the magnetism couples into through the boron insulators, and the hypothesis is that there's actually some phonons that carries angular momentum passing through, right? And that idea is more kind of corroborated more recently by putting a metal with a chiral material. So what happens is this is a like chiral insulator essentially, and by passing a heat, the only thing that carries heat will be phonons that with chirality, and then the system actually generates spins at this interface. So that would indicate that you have some phonon spin like conversion, right? Or even more recently, people demonstrated that if you shine light onto a ferromagnetic system with on top of some insulators, so somehow you can use the circular polarized light to talk with both the magnet materials and the insulators, and their interaction actually facilitate spin transfer and even like say magnetic domain reversal. So all this works, of course, show that symmetry-wise, it should happen, right? So because as long as you have chirality, it would couple with spin. But the main question for like practical application is how large are these effects? And then it turns out that all those systems have very weak coupling. Okay, so honestly, if you shine strong enough light, even if you measure the magnetic field of light itself, it will be on the order of a millitesla. Okay, so so that coupling was not very magnified. Okay. So then we would like to ask the question, can you find materials that by some physical mechanisms have much stronger coupling and thus facilitate this or kind of beneficial by taking this detour? So this is millitesla. Can we get Tesla by the same amount of light through phonons? So that's a question. And in fact, that question can be both experimentally searched and theoretically understood. Okay, so the way of searching such a strong effect would be using a phenomenological Hamiltonian. So here we're just saying that spin, this is the magnetic moment of spin, couples with the angular momentum phonons, basic chirality. Okay, so this is symmetry allowed because they share the same symmetry. And then from this, you do derivation. It will be effectively saying that the susceptibility of spin, which is affected by magnetic field, is proportional to the coupling constant and also proportional to the susceptibility of the phonons, which is what we call a phonon magnetic moment. That is to say that if we have a phonon that respond to magnetic field, then you will have the same phonon to generate very big magnetic field. Okay, because the quantum coupling is basically reciprocal, right? Okay. And then at least this part is pretty easy to do. Okay, so you just have a piece of material and put it in high magnetic field, and then measure the phonon frequency change. That's a Zeeman effect, or that gives a phonon essentially effective magnetic moment. Okay. So, and how large is that? You would imagine that these are ionic motion, right? So if you have an ion that rotates, and these are quantized, phonons are quantized, and then because they're very heavy, their magnetic moment should be pretty small compared with the electronic magnetic moment, right? So just as if you look at the nuclear magnetic moment, okay, it's 3 orders magnitude smaller because of the mass than the electromagnetic moment. However, these are very old experiments that shows there are certain materials whose phonon magnetic moment is actually bigger than electromagnetic moment. So that would be very counterintuitive. How come this very heavy ion, they carry that amount of magnetic moment, right? But anyway, so these are the experiments. Can see that all these are rare earths halide, very simple, very boring, paramagnet, insulating, like no like no electron correlation. Okay, but then when you apply magnetic field, the phonons exhibit giant Zeeman splitting. So these are typically electronic Zeeman splitting is on the order of 1 centimeter per Tesla. So these are about 10 centimeter per Tesla, right? Okay, so that's very big. And then what is going on, right? So it turns out that these materials are interesting because of some many-body interactions. Okay, so to understand that, you can imagine that. So this is a piece of material that has a single mode phonon, which is basically plane wave. And then the material has many, many local two-level systems. These are basically spin up and down. And then there's some coupling. Okay, so each spin can be flipped by a phonon. Okay. So what happens, interestingly, is that this whole piece of material has one phonon mode, because that's what like optics or plane wave optics can measure, right? So this momentum 0, you have the electric field, all the phonons actually move in the same direction. Okay, so there's only a single phonon mode that couples with light, but there are many, many spins that simultaneously couple with this phonon mode. Okay, so what happens is that coupling, effective coupling, is actually pretty strong, proportional to the number of your spin up or spin down electrons, which is very dense in the material, and proportional to this is a bosonic population of the phonon. And most importantly, it has a vacuum coupling. That is, even there is no phonon excitation, you have finite coupling. And if you have more phonons injected, you have more coupling. Okay. So that effective coupling between the many, many electrons and the phonons would mean that they form some perturbation. Okay. So the phonons move slightly in energy. The electrons also move in slightly in energy. Okay. They don't have to be resonant, although resonance will enhance your coupling. Okay. Now, what happens is, in this case, if we put electrons in this Hamiltonian, we start to put electrons with spins in the system. So we flip the electrons, spin, and then one of the coupling, because of angular momentum conservation, will become bigger because you have more populations proportional to the number of electrons. And the other electron level is depleted. So its coupling is less. Okay. In which case that you can see that the phononic state that carries different angular momentum will actually have different energy. So this is, and that difference in energy is proportional to how many spins you injected. That's essentially the effective Zeeman effect. Okay, and for this case, there's actually no limit in how much phonon angular moment or phonomagnetic moment, because as long as the electron is very susceptible to magnetic field, this is true for paramagnetism at 0 temperature. So you need an infinitesimal magnetic field to align all the spins. And then all the spin population will generate a giant splitting in phonon energy. Okay, so that basically gives you an infinite size of phonomagnetic moment. Okay, so that's basically the mathematical physics here. So that physics, so this Hamiltonian is called Dicke physics. It has a lot of very interesting properties that we can potentially engineer if we can control the phonon population. Okay. So in this case, then we set out to control the phonon population. Okay. And the way to control these phonons is very simple. Because these atoms, we want the atoms to rotate, right? Then you would need a field that also rotate at the same frequency of these atoms. Okay, which is not trivial because when we look at the phonon frequencies that are terahertz, actually a weird region for optical spectroscopy between the mid-infrared and far-infrared frequencies that in which you don't really have a laser source. Okay, so generating this pulses and then in a short period of time, and also manipulate its polarization is not easy, but assume that, forget about the technical details, but we did it. And then putting this pulse into the material would cause the atoms to actually rotate. And as expected, when the crystal field, the surrounding atoms actually start to dance like hula hoop, then the ions, the center ions, which is rare earth paramagnetic, you will see that the spin actually start to polarize as if it is placed under a magnetic field. Okay, so this is pretty nice. Everything is time resolved. You can see that the spins start to quickly develop when we inject phonons, and then when the phonons are dead, because all these of course, optical phonons actually live at picosecond level, and then the spins will start to relax again. Okay, so this typical paramagnetism. So from the spin dynamics, we put into the paramagnetic relaxation, then we can calculate, basically do deconvolution of the actual field that has been generated by phonons. Okay, so from the magnetization dynamics to the field dynamics. Okay, and then here's the result. So we know that the phonon doesn't live very long. So if we inject light into material, phonon lives about 1 picosecond, or maybe even less. And then they pretty much generated a field profile extracted from experiment, similar to what we expect in theory. Okay. So what does that mean? If you look at the feature, first is that we are able to, yes? These dynamic field are not from spin. So here, origin is paramagnet. Okay, so there's no net magnetization. And then the phonons create an effective magnetic field that polarize some of the spin. The net spin only generates very little magnetic field. That's negligible here. This is only from the phonons, yeah. So here, so first we can manipulate like a pretty big field in picosecond, and hopefully by choosing material parameter, you can have longer and shorter time. So actually, in the same material, we can find other phonon modes that live hundreds of picoseconds instead of 1 picosecond. So there's some tunability, but also importantly is that we are able to get the Tesla field. Okay. So that's bigger than any other materials. Okay, and what's better is that with big lasers, if we're as rich as rubber, then we'll be able to get even larger field. Okay, within materials. So that would be very useful already for studying a lot of like high field phenomena, hopefully in condensed matter. Okay, of course, there is limitation because fortunately, for all this optical spectroscopy, it's much better working insulators, which for a lot of condensed matter theorists, it's not very interesting. But so consider if we're working with spin liquid, for example, then you can actually study how their behavior at very high fields. Okay, one example. So it's great to have a particular material that holds very strong magnetic field. But the material itself is pretty boring. It's paramagnet, right? So it's not going to, you cannot generate devices based on that. So we would like to ask a question, if we have a real ferromagnet, say 2D ferromagnet, which is going to be useful in 2D spintronics, and can we use that field in some way? Okay. So so we just deposit some like van der Waals 2D magnet onto onto our substrate, which has chiral phonons, and then see what happens if we create chiral phonons within the material. Okay. So the result is pretty exciting because, of course, if you put lasers into the material, you will always heat things up. Okay, so originally temperature is 10 Kelvin, we raise to 30 Kelvin. So that would cause some thermal demagnetization, right? And also because this chiral phonon generate huge magnetic field within the substrate, you have a pretty large spin response within the substrate itself, right? But the interesting thing is that if we probe the spin dynamics in the heterostructure, which is the red curve here, it is slightly bigger than the summation of the two materials put separately. Okay, so there's something happening at the interface when they join together. And what's happening there? So here are some features. Okay, first, we study the difference between like exciting the sample with just heat, which is linear polarized terahertz, no magnetic field, or you put heat plus magnetic field. This is circular polarized terahertz. Okay. So we find that if you put small amount of energy, nothing happens, okay? Nothing exciting happens. And there is a threshold above which if you heat enough, you will have spin dynamics, okay? So this is kind of expected. So think about that. If you have a perfect magnet, perfect ferromagnet at 0 temperature, and no matter what you do, the spins are frozen, right? They won't respond. So only when you raise the temperature, kind of loosen the spins, now they start to respond, okay? That's first important feature, understandable. And the second feature is if you look at the difference between these two curves. So if you sum green and blue curves and compare it with the red curve, there's a relatively slow difference, okay, that changes on the order of, say, tens of picosecond. So this is kind of surprising because the field that we generate is 1 picosecond. The thermal dynamic, the thermal diffusion, if there's a pure thermal effect, is on the order of tens of picosecond, okay? So what can happen like on the order of 40, like tens of picosecond? It will be the spin generated from the substrate itself, okay? So that is to say, so these are the actual difference. You can see, text is too small. So this is 0, this is 50, this is 100, okay? So you can actually see that the noisy curves are experiments. So if we just inject heat, you have some thermal demagnetization here. Then if you generate circularly polarized terahertz, basically adding more effective field, then you can either enhance that demagnetization or completely suppress that demagnetization, okay? And because the slope here, dynamics is pretty slow, we would expect that this dynamics is not directly related to the effective field from the phonon, but it's a sequential event. So phonon generates spin in substrate, and then spin kind of affect the ferromagnetism in the heterostructure. Okay, so that model sounds like pretty reasonable. So then we do a atomistic simulation, which basically says the spin dynamics of the ferromagnetism is related with how you apply an effective magnetic field in the nearby materials, okay? And then that will indeed, and that we assume that the effective magnetic field is lasts about 40 picoseconds. That number we know. Okay. And here's a result, which is pretty surprising. First, we can almost reproduce what happens, except for two features. First, the effective B field required for switching or for generating a spin dynamics is bigger than the effective field in the bulk material itself, which is counterintuitive, right? So how come that this phenomena amplifies magnetic field? And second feature that does not agree with the experiment is that after the field is gone, you would expect that all this spin dynamics relaxes, right? So eventually, regardless of whether the field is positive or negative, they will converge to no field, like just thermal effect, right? Okay. But in experiment, you can see all these three curves do not converge. Okay, so in reality, there is some persistent spin dynamics that cannot be explained by if you just have a simple heterostructure. Yeah. So what actually happens within this material, so we did some further simulation, is that this is a very soft magnet. And then at zero field, it actually forms magnetic domains, okay? So you have positive domains and negative domains. If we apply an effective magnetic field in positive and negative domains, they respond, but very little, okay? However, the spins, a little external magnetic field is really effective in pushing the domain boundaries. okay? And then that movement of domain boundaries is persistent, okay? So can you imagine that, so once the pulse comes, domain boundary moves and it stays there, right? Pretty much like even when the field is gone, it still stays there, right? So that kind of time dynamics agrees better with our like observation, but we're still trying to make it a quantitative agreement at the moment, okay? But then we're pretty sure that, yeah, so it's a pretty complicated phenomena. We have chiral phonons, we have ferromagnetism, and we need domains, okay, which is a key part of any spintronics. So let's switch gear a little bit, not looking at the spin itself, but the spin waves, okay? So spin, of course, is pretty useful, but then if we want some coherent spin dynamics, then it will be basically spin waves, right? And then the spin wave has at least one benefit, is that it can directly couple with phonon. So for example, if we have a single phonon, then it will be just directly converted to a single spin wave. You cannot convert a spin to, I'm sorry, you cannot convert a phonon into a single spin, but you can translate fully its angular momentum of phonon to fully the angular momentum magnons. This is one-to-one, right? So that is, in many cases, more efficient. And then what the other thing that is interesting to magnum-phonon coupling instead of spin-phonon coupling is that magnum-phonon coupling can even occur at 0 temperature without putting external light. Okay, so think about that. If a piece of material, so previously we put light, excite chiral phonons, and then chiral phonons will generate spins, right? Okay, but in a materials where you only have phonons and magnum modes, so they're bosonic excitations, no population. But then because of uncertainty principle, you will always have phonon, oh, here. It's slow, okay. You will always have phonon fluctuation, which is equivalent to half of the phonon that couples with magnum fluctuation, which is half of the magnum. Okay. So that's pretty interesting. And this, what we call a vacuum coupling, would actually cause some pretty unusual phenomena. Okay. So in order to see that type of coupling, we would still like to go to 2D materials because we're doing optical studies. Okay, so we're only looking at zone center, a gamma point, 0 momentum. And then low dimension materials have finite density of state, which enables larger coupling for these type of excitations. Okay, so we're pushing to the limit. We have a piece of monolayers exfoliated from antiferromagnet. This is iron phosphor selenide, which has this antiferromagnet structure. Okay, so you have half of the iron spins pointing up and half of the iron spins pointing down. Okay. And this antiferromagnet has antiferromagnet magnons, and of course have structure oscillations as phonons. So in this case, then what we found is that both magnons and phonons have field dependence, which means that they both have pretty large angular momentum, okay, and magnum moment. Not only we see a pretty large quantum cooperativity, at the time of this paper, this was the largest number found in any materials, but also if you have coupling, then it would predict that the two magnum bands and phonon bands, when they cross, they will actually support topological gaps. So the idea is that you have, so in this material, because of the symmetry, we have symmetric phonon modes, symmetric magnum modes, and anti-symmetric phonon and magnum modes. So typically, so these are two groups that don't talk with each other. So that's why there is a protected crossing. And then you don't have to put in any phonons and magnons. this 0 temperature, but just because of the vacuum coupling, if we apply magnetic field, it will break the symmetry that causes the symmetric and antisymmetric modes to talk, and then the talk opens a gap. Okay, because this is a magnetically induced gap, this gap actually breaks time reversal. And then if you calculate the Chern number of the bands, it actually is non-zero. Okay, so essentially this is pretty much like the quantum Hall effect, where you apply field and then you generate actually Landau levels without with finite Chern numbers. Okay, so that means if the material has spin lattice coupling that generates this magnon-phonon hybridization, they will be essentially become topological just by itself. You don't have to inject any phonons or magnons. It will become topological, okay, because of coupling itself. So I think I'm running out of time, but I would like to just quickly mention something that is very special with phonon-magnon coupling. Okay, so in one material which is predicted to have chiral phonons, we pretty much did the same experiment to put circle polarized terahertz light into the system in the hope that to generate some magnetic moment, just as the case of cerium fluoride, and the effect is pretty disappointing. So with different circle polarization, there's actually nothing difference happening. But pretty surprisingly, no matter what type of polarization we put inside the material, we always see a very big spin effect within the material. Okay, so as long as you put phonons, and then there will be spins generated, and that the amount of spin generation, if you calculate the magnetic field, it's actually much bigger than chiral phonons. Okay. So what's happening there? The material itself, cobalt titanate, initially is a symmetrical material. So which is to say that no matter how you distort the atoms, it should really not generate a finite spin. Okay, because initially this is a magnetic material, but it is AFM, and you can prove that it preserves time reversal symmetry. So you shake lattice. If the shaking of the lattice does not break time reversal, there shouldn't be any spin. Okay? But what happens is this is a bulk piece of material and it has surface state. And it turns out that the breaking of surface symmetry actually is sufficient to generate what we call the spin seebeck effect. That is to say, you shake the lattice, effectively the flow of phonons is just like the heat flow. Okay, and then that generates a spin flow. The spin keeps flowing, so even if the heat dissipation is gone, the light is gone, the phonon is gone, and then as long as there is a flow, the spin keeps generating at the interface, and that creates a pretty large, actually pretty unexpected spin effect. Okay? So that basically says that whenever we consider the symmetry or chirality of the material, the presence of surface actually plays a very important, even extrinsic role, but that extrinsic effect could be much larger than the intrinsic symmetry of the material. So let me wrap up. No, time is limited. If we can control lattices that breaks time reversal, then you could consider it's a new way to engineer materials. Okay, so it can be applied to many types of materials. So the practical limitations of how much phonons, how many phonons you can put into materials can be manipulated by basically photonics, where you can crank a lot of energy into a small volume. You can also consider to make cavities and that breaks time reversal. And then these cavities will actually greatly enhance light-matter interaction that would allow the spin phonon coupling to happen even, again, without external excitation. So just enhancing the quantum fluctuation, it may even produce chirality within the material if you have a chiral cavity. Okay. So with that, I would like to first thank the students who did the experiment. We have theoretical collaborators, and the sample growers, and external collaborators, funding agencies. Thank you very much for your attention.
Very much for the nice talk, and it's open for questions. I should say in the beginning, we do have, like every colloquium, a raffle where we have a raffle prize. So for the students who ask questions, so if you do, please come down here after the Q&A. So it's open for questions. Yeah.
Great talk. On your slide for potential for ultrafast spintronics, you had time resolved magnetization.
Yes.
Further back.
Oh, okay. Yes.
What causes the secondary peak?
Oh, okay. Yes. So our terahertz is actually not a single frequency. So this is a limitation because water in the air actually creates a dent in spectrum. And then that creates an interference effect in time domain as well. So this is because of the secondary pulse that comes, but so that's why it's included in the Phonon model. We actually excite a secondary little pulse there. Yeah.
Yeah, related to this same thing. What degrees of influencation you guys have?
Yes. So in this work, it's tiny. So the reason is this material is paramagnet, and then the amount of spin generated by a given field also depends on how long the field's duration. So if it's a pulse field, yes, it's big, but then most of the spin do not have time to respond. Okay, and also this is relatively high temperature. The lower the temperature, the more susceptibility of the spin. So technically, yes, we can push the amount of spin bigger, but in this case, it's not very large. But what's surprising is that once we put this little amount of spin into the 2D ferromagnet, there the effective change of magnetization is actually on the order of 10 to minus 2. Okay, so 1% of spin. So that would mean that here the domain wall actually moves relatively little. So about 1 nanometer within the process. But then because this is a very soft magnet domain, it's very fractured. So in total, we have a bigger effect. Yeah, but so this effect can be magnified if engineering properly.
Yeah, kind of a bigger picture question that they're asking. So for studying the Phonons, are you limited to optical spectroscopy, or would you be able to do any insights from electron spectroscopy or ultrafast fluorescence spectroscopy?
Very good question. Yes. So the field of this chiral phonon is rapidly advancing, essentially booming, partly because the theorists are coming with all types of theory, but also because many probes have been applied to studying phonons. So if we go back to the very beginning, about the many types of chiral phonons here. Okay. So for example, structural chirality, people have probed by, let's say, X-ray scattering. Or for the electron, so for the chiral phonons coupled with spin, potentially can probe with neutrons as well. Although neutron has not been done, we're trying to do some experiment there. Electron microscopy, pretty similar as X-ray, but it has more advanced because it has much better resolution. So today I actually discussed with Sandia on the possibility that these phonons can be directly seen within electron microscope. So people have tried to use, let's say, beams for example, to see chiral phonons. I think there's another work. One very important, transport. Okay, so all this thermal Hall effect, essentially people have, if it's coming from phonon, then these are also chiral phonons. Yeah, so in many ways, yes. Yes. So this is a very interesting question because no quarter wave plate exists for this type of a wavelength. Okay, so in terms of generation, that's not developed by us. So the pulse itself, this is called difference frequency generation. You put two near infrared pulses together, and the difference frequency is set to, in this case, 10 terahertz. Through nonlinear crystals, it will create a pulse. Okay. So then the next thing is actually pretty simple. If we split the two pulses and then into orthogonal polarization and then delay it, then create a circular, right? But that has to be manually done. Yeah, so that's how we do it here.
Maybe on the final part, we talked about the Magnon.
Yes, yes.
Phonon coupling.
Yes.
So what is driving that interaction there? Spin Magnon coupling.
Yes. So
iron phosphor selenide, right?
Iron. So in this case, cobalt titanate. Yeah.
Oh.
Cobalt titanate. Yes. Generally, any materials, magnetic materials, should have some spin phonon coupling. Right? So for this materials, what is believed, we didn't really go into the microscopic theory. What is believed is that yes, so once we have phonons, you should, and we actually see it. So these oscillations are phonons. So atoms start to move, and you can see on top of that oscillation, there is some envelope. So these envelopes are actually magnons. Okay. So yes, basically we're pressing the materials, and you will see the spins actually oscillate. Right. So that's very understandable. What is not understandable, more complicated, is that why in a very long time there's a net spin generation. So, and here we just use phenomenological models. So assume that there is a spin seebeck effect, which means that the magnetization is somehow proportional to the heat flow. Okay, and then that would agree with the time dynamics we see here. But then, so spin seebeck is pretty general in, let's say, ferromagnetic materials. But then why this piece of material being an AFM, and it actually does not break time reversal in its bulk form, have a finite spin seebeck effect? That's a mystery. And we can only hypothesize that from symmetry argument, the surface does break symmetry. So that reduces the surface magnetic group to essentially no symmetry. Okay, so that would be compatible with spin seebeck effect. But exactly why spin does this, we're not sure.
Yeah, well, thank you very much. If no more questions, let's thank Hanyu again for this excellent talk.
Thank you very much, Robert, and thank you very much for your attention.